We have constant acceleration. What's that mean in terms of motion? ROC stands for rate of change, and implicitly rate of change of V with respect to T. How do you write the rate of change of V with respect to T? Think about that for a second, and I'm going to write it down. Now, if you don't know the answer to that, you didn't understand calculus. It's the most basic thing in calculus, depending on how it's developed. You can develop in terms of integral. It's just a derivative. Rate of change of V with respect to T is dV dt. That's why you did all the limits. That's why you developed the whole theory of what a derivative is. Which everybody that takes, nearly everybody takes calculus then immediately forgets, because you get all tied up in learning how to apply the various rules, the chain rule and so forth, and then some more complicated problems. You lose the sight of the forest for the trees. All you're looking at is the trees. You're not looking at the big picture.
Come on down to the green house.
So you want to avoid that. If you're taking calculus, good time to avoid it. If you're taking multivariable calculus, it's a good time to really nail it down. Okay? And that's exactly, I think, what our last assignment was about. Getting derivatives of functions of many variables, limits, all that stuff. Actually, the next assignment really gets into your partial derivatives. But anyhow, that's what we got. Rate of change of V with respect to T is dV dt. Okay? Now, think it again. If the derivative of V, which is a function of T, is constant, then what do you know about that function? Don't say I got the camera on. But if you know, jot it down. What do you know about a function if its derivative is constant? I'll give you a little time to think about it. Especially if you're just taking calculus, it's not the way you generally look at it. If I give you a function whose derivative is constant, can you write down an example of a function whose derivative is constant? I want to use A here. If dV dt is A, what's a function whose derivative is A? I mean, yeah, we don't have to say if dV dt is A. dV dt is A, so what's an example of a function whose derivative is A? Well, I can think of one real quickly. We'll agree that the derivative of AT is A. Is that the only function whose derivative is A? Well, if the derivative is A, then the multiple of t has to be at. It gives you derivative a. You can't have another t term in there. But you can also have a constant term, because the derivative of a constant term is 0. Doesn't add anything to the derivative. Okay?
And so, yeah, well, yes, anyway, so you now.
Well, if v of 0 is v naught, that's what we generally use. If v of 0 is v naught, then v of 0 is also a times 0, which is just 0, plus a constant. So your constant is v0, right? All right.
We'll see that comment for another day.
Now I could quickly talk about that in terms of integration, but my first year calculus course hasn't gotten integration yet, I don't think. Coming up fairly soon, I think. Okay? So if you understand integration, you just see this constant as your integration constant. And this is, this is just something you solve by integrating. You just integrate a with respect to t, you get at plus an integration constant. And you interpret the integration constant as your initial velocity. Your integration constant is v of 0. If you plug 0 in, that's all you're left with. Okay, well, v is the rate of change of x with respect to t.
Probably like 14 to 18. So count backwards from December 14th.
So x is dv dt.
What can we produce two sides
And I wrote that down backwards. Thinking ahead to the next step, it just wasn't going to work out. And if you interpret v as the rate of change of x with respect to t, the rate of change of x with respect to t is clearly dx dt. Don't be like me and write things down without any mental activity. My hand did that, I didn't. Okay. So, actually, did I say that right? Yeah, I did. I don't know if I said that right or not. Anyhow, v is dx dt. I think I wrote that down wrong. If not, I just looked at it wrong. Okay, v is dx dt. So dx dt equals at plus v naught. Now, can you write down an expression whose derivative is at plus v naught?
sexual propagation of using C to the asexual propagation of ultrasound, which is funny or really for our
Well, it's fairly simple.
later in.
Can you write down an expression whose derivative is AT?
So it-
Well, what happens when you take the derivative of a power of t? You get the next lower power, right? So your derivative must give you power 1, right?
That's another kind of topic that's open for debate.
So
What is a cell?
your x function has to have power 2.
You gotta flip that around.
What power 2 expression gives you AT? Called an antiderivative, incidentally, but if you haven't gotten to that, you don't have to use the terminology. Okay, well, I'm going to tell you. Everybody can verify if the derivative of 1/2 AT squared is AT. If the derivative of t squared is 2t, and the 1/2 times 2t just gives you a t, you end up with an AT. Okay, well that gives you the AT.
But on the marketing.
What about V naught?
You know, we try not to.
Well, what's your power t here? It's the 0 power, right? Well, you can figure that out. It's obvious
In our plant cells in the past, we just.
that V naught t has a derivative that's equal to V naught.
So we added.
And then, just as before, there's a constant term, because if you take the derivative of a constant term, you get 0. So if you want to write the most general possible function, whose derivative is AT plus V naught, it has to be like this. If you're letting x naught stand for x of 0, then of course you plug in 0 for t, you get 0 here, 0 here, but you still get your constant, which is a good thing because that constant's going to give you your x naught. There you have it. And the steps are very, very simple. Now, if you've completed calculus, you can see this is just integration, and you have integration constants. If you haven't completed calculus, just, if you've got to look at the video again, think it through, do so. Think it through until it's obvious. It'll give you more insight into derivatives. And then when you get to integration, you're going to have a big head start. It's going to be worth your time in the long run. It'll save you as much time as it takes. Sort of. I mean, I can't really predict that. It might save you more time than it takes. Okay?